Hey everyone, we have a little bit different environment today in that I'm going to be hanging in my basement coming to all of you for the next several lessons. We don't have a ton of work yet to do for the year, we're just a few weeks out, and with you guys basically being done a week before anyone else, that puts us in a pretty good position, but I still have a whole nother chapter for sure to cover um, of material here. We're going to go ahead and jump across chapter 7. I would have skipped chapter 7 either way, and we're going to jump into chapter 8, and that's pretty much where our journey is going to stop for the year. But I did want to get into and through chapter 8, which is a pretty short chapter. It's only a 3-section chapter, and the first 2 are more important than the third one, but we'll get through all of them, and we'll be able to get a review and a test in. Not that it's a test. It'll be more like a open book, open notes quiz thing that you'll work on at home and together if you want to, and with Mr. P if you want to. So it's more like a worksheet, but just like the chapter 6 test was. Today we're going to be in chapter 8, lesson 8.1. We're going to be talking about limits at infinity and L'Hopital's rule. And the concept is fairly simple once we get going, but I want to kind of talk about it to pull you guys through the idea first, and then I'll release you into homework later. I don't think the homework's going to take all that long, but the concept is pretty important. So I want to go ahead and lay enough groundwork that we kind of understand everything that's going on. Hopefully everything's going well with you guys, and everything's going well in the class. It should be still late April or early May when you're watching this, hopefully. So we're still we got a little chunk of time left in this. At this point in time, we're still talking about the possibility of May 1st being the end of this, but I think, and a lot of people think that this is gonna roll on through here. All right. So what we're talking about is we're talking about limits at infinity. So much earlier in the year and into last year, you guys talked a lot about limits as x approaches some value of a function. Let's say that our function is 3x plus 6, and I want to find the limit as x approaches 2. Well, what I'm asking is, in this line, when it happens to be a line, it starts at 6 and goes up 3 over 1. So it looks like this here. And what it's asking us is, as the graph approaches 2, which is on the x-axis, what would the y value be? And in our case, because this line is nice and solid, that's not a problem whatsoever. My graph didn't get nearly steep enough because it should have been up 1 over 3, so it should be more like this rather than what I did. So it'll be up in here somewhere. So I'll just go ahead and drop 2 into the equation because that's not a problem. And I have 3 times 2 plus 6, which gives me 6 plus 6, which is 12. That is the limit as x approaches 2, which is, not very difficult to look at. And then we talked about things that had limits, but were not calculatable. Things like things like x squared plus x squared minus 9 over x squared plus 6x plus 9. and then we're going to go the limit as x approaches 3 here. Now, negative 3. I need to flip these. So now on the bottom, what I'm looking at is x plus 3, x minus 3. If I put negative 3 in, this factor right here is 0. And that's an issue because it makes the whole denominator of this 0, which means that when I put in negative 3, I'm going to get an undefined value, x squared plus 9, x squared minus 9. So on the top, I have a value. I have 9 plus 18 plus 9, which is 18 and 18, or 36. But on the bottom, I have negative 3 squared, which is 9, minus 9, I have 0, which is undefined. However, the graph does have a limit at this point because the top also factors into x plus 3, x plus 3, and here the x plus 3 part will cancel each other out. So this function mirrors a function that is x plus 3 over x minus 3. Now, it's important to remember that the function still doesn't have a value at negative 3. However, because these two pieces factor out, now when I put in my negative 3, I end up with 0 over negative 6, which in fact does work. It's 0. So the limit as x approaches negative 3 is 0. But the actual solution at negative 3 is undefined, which tells us that this function has a hole in the graph. And I know because you have a squared over a squared that this is some sort of linear looking function with a hole in it at that moment, at that negative 3. But now what they're asking us to do is they're asking us to bring this concept to a new level. And instead of talking about limits at specific values, they want us to talk about the limit as x approaches infinity, or the limit as x approaches negative infinity. So, in other words, what's happening to the y values if I go way, way out in our functions? And when the function's simple, this is really easy to figure out. It's when the functions get more complex that we start focusing on L'Hopital's rule to talk about how they look. And L'Hopital's rule actually makes things very, very, very complex things very simple to figure out. So it should go pretty smoothly. But let's focus on just a couple of quick examples so you know what I'm talking about here. So let's say that I want the limit as x approaches infinity of x squared. So what we're sitting on here is a parabola. Looks like this. And the question is, as I go further this way, way, way out, where are the y values going? And this function just keeps going up and up and up and up and up. So as my x value goes to infinity, my y value is also going to infinity. It's just shooting upward forever. So the limit as x approaches infinity of x squared is in fact infinity. That is the solution to to this situation. As we go further out, this function goes way, way upward. Now, similarly, we could be working with some sort of cubic function, let's say x cubed plus 3. So that function looks like this. Again, as we go further to the right down this function, the y values are shooting further up. So as x goes to infinity, y goes to infinity. Another way to look at this is to ask myself, okay, so if I start putting numbers in this, where am I headed? So if I put 0 in here, I have 3. If I put 1 in here, I have 4. If I put 2 in here, I have 11. If I put 3 in here, all of a sudden I have 30. And then this starts really expanding. If I put 4 in here, I have 67. And then 5 would take me to 128. So it's going bigger and bigger and bigger and bigger and bigger. And it's not only is it getting bigger, it's getting bigger faster and faster as we go, expanding toward infinity. So the limit as x approaches infinity of this function is also infinity. So the question is, are all functions, so if I just, say if the limit as x approaches infinity of every single function is infinity, right? I mean, is that true or is it not true? Well, let's look at the function negative x squared plus 2. So this is a frowny face parabola because you have a negative a value. So it looks like this. Oh, I moved it down though. So it actually looks like this. Frowny face parabola here. So as you can see from my picture, as I go further to the right, instead of going upward, this one is in fact going downward. So as we go further and further to the right down this function, our y values go further and further down, taking me not to infinity, but to negative infinity. So now those are only two options. Well, let's walk this one out before I bird walk away from this. So let's say that I put 0 in here. Well, 0 squared is 0 and plus 2 is 2. And then 1 squared is 1, make it negative, plus 2, that's 1. If I put 2 in here, I have negative 4 plus 2, which is negative 2. If I put 3 in here, I have negative 9 plus 2, which is negative 7. If I put 4 in here, I have negative 16 plus 2, which is negative 14. If I put 5 in here, I have negative 25 plus 2, which is negative 23. Already, I am rocketing downward toward my negative infinity, just like we were talking about a second ago. So now I'm going to re-ask the question that I posed a second ago. And by the way, I know I have very limited board space. Feel free to pause this, and write the things down that I'm doing. A lot of the stuff I've done so far hasn't been super important to what you're going to do, but it's going to build. So make sure that you're pausing me and copying things down as you need, so that you don't get overwhelmed by all of this. So the question I posed a second ago is, do all of these functions then do they always equal infinity? And the answer is no. Not every function equals infinity. If we have the limit as x approaches infinity, infinity or negative infinity. If we have the function as x approaches infinity of, let's say, 3 to the negative x power. Here's a function that has a shrinking pattern. This is an exponential decay function. So on this side, it starts really, really high up, and then it shoots down, and then it comes across like this. And I know that because I know that, but I also know that because the negative power forces fractions in. So if I put 1 in here, I have 1/3 because I have a fraction of my 3. If I put 2 in there, I have 1/9. If I put 3 in there, I have 1/27. If I put 4 in there, I end up with 1/81. And what's happening is this function is shrinking. But it's not shrinking toward negative infinity like we were seeing in the last example. As we move further and further down the line this direction, what's happening is this is slowly getting sucked smaller and smaller down toward 0. So instead of this carrying to infinity or to negative infinity, it actually levels itself off and ends up at 0. The limit of that function is 0 because it's slowly shrinking downward. So the question right now is, how do we know? How do we know what's going on with the functions? A lot of it is really rooted in their graphs, but more importantly, we're going to know a lot long term by using L'Hopital's rule. But let's just start with our basic list of things that we know. So first off, already we know the limit as x approaches infinity of a polynomial that has a positive a value, no matter what the polynomial is. I did an x squared and an x to the third, but let's say x to whatever, n plus x to the n minus 1, etc. So in any polynomial down to a constant term. So this could be x cubed plus 6x plus 8, or it could be x to the 8th plus 12x to the 7th, etc., all the way down to maybe 7. It doesn't matter what the polynomial is. The key is that this first value is positive. If your leading coefficient is positive and you have some sort of polynomial, that limit is infinity. If you have a limit as x approaches infinity of some sort of negative polynomial, so your leading coefficient is negative, whatever the polynomial is, whatever the powers are, it doesn't matter. This negative right here, the leading coefficient, controls the entire answer. It's pulling that entire polynomial down, because what's happening is this polynomial is smiling. No matter what it is, it's facing up, coming through, which is pulling the y value to infinity as x goes to infinity. This polynomial is frowning because of the negative leading coefficient, so it's pulling that y value down as x approaches infinity, no matter what. That's how it's panning out. So we have infinity here, negative infinity here. Done deal. What about the limit as x approaches infinity of something like an e to the x? Well, we know that an e to the x is a exponential growth function, like the function I had up earlier, only the one I had up had a negative exponent, which made it decay. This one has growth. So if the exponent here is positive on this is a growth function, and what's happening is it's shooting upward toward infinity. This is the opposite of what we had before. It comes across really level and then it shoots upward. Now let's re-talk about the one that we were working on earlier. What about the limit as x approaches infinity of e to the negative x, which is any exponential decay function? So as we saw earlier, these exponential decay functions, whether this is e or 2 or 3 or 12 or any number sitting down here, what happened was when they ran off toward infinity, we ended up with 0. They were panning off toward the x-axis. Again, we started high, dropped down toward the x-axis as we shot across, right? So we ended up with 0 on those. Another couple of basic ones that we're going to work with are the limit as x approaches infinity of the log of x. So if we have a logarithmic function, what that looks like is it's like an upside down e function. They look like this, exponential growth. As we're headed this way down our x-axis, this value is growing, and it's growing really, really slowly, but it is growing upward. So this is in fact headed toward infinity. Again, if you had the opposite of that, if you had a negative log, it would flip and it would go the other way. It would go downward rather than upward. Hopefully all of that makes some good sense. So now that we know that polynomials with a positive leading coefficient are headed toward infinity, polynomials with a negative coefficient are headed to negative infinity, e is headed to infinity, e to the negative x is headed to 0, and logarithmic functions are headed toward infinity. Now we can really piece this together, because what big picture is really going to happen, this is all pretty basic, you could just have thrown them in your calculator and figured them out, is how do we know what's happening when we have functions that are kind of a mashup of multiples of these? So what is the limit as x approaches infinity of something like x squared plus 6x plus 8 over x minus 12? Now, the key to this is to pay attention to what piece of this, numerator or denominator, is going to ultimately have more power in this function. So short term, they both have fairly equal power in the early movements. If I put 1 or 2 or 3 in, both of these are balancing each other pretty well. But what happens is, ultimately, as we go further and further out, the top part of this function, the numerator, has more power than the denominator. And the reason for that is because it has a higher power. The larger exponent in the numerator is eventually going to outpower anything this denominator has going for it, which is going to take this function and allow the numerator to take control. So ultimately, because the numerator has the higher power, I'm only going to focus on what my numerator tells me. And my numerator is going to infinity. because my numerator is going to infinity, I'm going to end up with infinity over anything. And infinity over anything is infinity. The top will win. What will happen is eventually you're going to have like 100 quadrillion sitting on the top, and you're going to have like 10,000 sitting on the bottom. The bottom is growing so slowly. It grows by 1 each time. But the top is squaring the number and then multiplying it by 6 every single time. So it's growing much, much faster than the bottom is growing. And so it's going to take over and just take off. So if the top wins, we look at the top to take us where we're going. If the numerator wins, we look at the numerator to take us where we're going. If the numerator was negative, because of a negative a value, it would be negative infinity. Because the numerator is positive, it's pulling us to infinity. Now, what if this was reversed? What if I have the exact opposite? The limit as x approaches infinity of x minus 12 over x squared plus 6x plus 8. Now the bottom has more power than the top. So that tells me that I have this rinky-dink tiny number on the top and this gigantic number on the bottom. So I have this huge infinity down here, and then I have some tiny number up here, right? Some small thing up here. So what ultimately is happening here? If I have an infinitely large number in the denominator and a small number in the numerator, what that's telling me is this is headed towards 0. As this pulls further and further out, because my denominator is getting huge, instead of having a billion over 100, I have 100 over a billion. Well, that is epically small, but epically small not toward negative infinity, but epically small towards 0. If your denominator is winning, you're headed towards 0. Now, the fun thing with the denominator winning is it doesn't matter if the denominator is positive or negative. If you have a positive leading coefficient or a negative leading coefficient, because 0 is 0. So it makes no difference whatsoever. Now we got to look at a couple of other quick things, and then you'll be ready to go here. Okay, so what if they balance? Limit as x approaches infinity, and I have like 3x squared plus 7x plus 8 over 2x squared plus 5x plus 10. All right, so they're exactly the same. X squared over x squared. Here's where L'Hopital's rule comes into play. What L'Hopital says is if the top and the bottom are in perfect balance power-wise, in other words, the highest, the degree of both is the same. The highest exponent is the same. What you need to do is you need to take everything but the monomial with the highest power, your degree monomial, and just get rid of it. None of this will affect the problem at all. None of that. So we just get rid of it and we isolate the other two pieces. 3x squared over 2x squared. Now we're going to take these two remaining pieces and take their derivatives until we have nothing but numbers left. So we don't want any variables at all. So the derivative of 3x squared is 6x. The derivative of 2x squared is 4x. Derivative again, 6 over 4, which reduces to 1.5. That is the limit as x approaches infinity of this function. That's where this function's headed. That's how L'Hopital's rule works. Eliminate everything but your highest degree elements, and then take the derivatives down until you've wiped everything else out. Now this is really going to help us moving forward to talk about what's gonna have more power when we're not dealing with polynomials, because we do have two non-polynomial cases that we deal with, e and ln, and the key is their derivatives. So if we're dealing with an e, let's say that we have e to the x over x to the third. What has more power, e to the x or x to the third? Well, L'Hopital's rule will help us pan this out. So if I start taking derivatives of this, the derivative of e to the x is e to the x. The derivative of x to the third is 3x squared. If I go again, the derivative of e to x is still e to the x. But the derivative of 3x squared is 6x. Now if I go again, the derivative of e to the x is e to the x. And the derivative of 6x is just 6. Already you can see this piece it's not going anywhere. That gives it all the power. E to the x is always going to win. E to the x always wins. So if e to the x is in the numerator, the answer is either infinity if it's positive, or it's 0 if it's negative. Done deal. 100% of the time. If e to the x is in the denominator, the answer is 0. 100% of the time. Because e to the x always wins. Now, what about ln? Let's have the same situation with an ln. So let's say that we have ln of x over x to the third. When I use L'Hopital's rule and I take the derivative, ln of x's derivative is 1 over x. And x to the third's derivative is 3x squared. Well, what happens is this ln immediately drops to the bottom with my x squared, making it 1 over 3x cubed. And now all the power is in the denominator. So ln x always loses. Whenever you see an ln in a problem, the other part is going to win. So in this case, the ln's in the numerator, so the denominator wins. So the answer to this is 0. If the ln's in the denominator, then immediately I know the numerator is going to win. So whatever I have in the numerator is going to tell me I'm either going to infinity or I'm going to negative infinity. And if you have an ln up against an e, oh, that ln loses badly. I'm going to follow this video up with another video to get you into the homework, but hopefully that gives you the setup for everything we're going to talk about here with L'Hopital's rule. I'll do a couple examples and start the homework with you in the next segment.